Imagine for a moment that you are holding a perfect crystal in your hand. It is clear, cold, and heavy, a lattice of atoms arranged in a flawless repeating pattern that extends in every direction. This is a space crystal. You have seen them before: diamonds, salt, snowflakes. They are beautiful because they are orderly, because the same molecular structure repeats over and over again, creating a symmetry that our eyes find deeply pleasing. Now, I want you to imagine something even stranger. Imagine a crystal that does not just repeat in space, but repeats in time. Imagine a structure where the pattern does not just extend left and right, up and down, forward and backward. It extends forward and backward in time itself. Every second, the crystal returns to the same state, ticking like a cosmic metronome, forever oscillating without ever losing energy. This is not science fiction. This is a time crystal. And for the past decade, time crystals have been one of the most fascinating and controversial ideas in all of physics. The concept of a time crystal was first proposed in 2012 by the Nobel Prize-winning physicist Frank Wilczek. He was thinking about the nature of symmetry, one of the most fundamental concepts in physics. Symmetry means that something looks the same even when you change it. A circle looks the same when you rotate it. A sphere looks the same from any angle. A perfect crystal looks the same when you shift it by one lattice spacing. Wilczek asked a simple but profound question. If space has symmetries, and if crystals break those symmetries by creating a repeating pattern in space, then what about time? Time also has a symmetry. The laws of physics are the same today as they were yesterday, and they will be the same tomorrow. This is called time translation symmetry. Wilczek wondered if it was possible to break that symmetry, to create a system that does not look the same at different times, a system that oscillates forever in a perfectly regular pattern. He called this hypothetical object a time crystal. For years, time crystals existed only on paper. They were a mathematical curiosity, a thought experiment that seemed to violate the laws of thermodynamics. How could something oscillate forever without any energy input? That would be a perpetual motion machine, and we all know that perpetual motion machines are impossible. But Wilczek and his followers argued that time crystals do not violate thermodynamics because they are in their ground state, their lowest possible energy state, and they are simply stuck in a cycle. They are not losing energy because they are not doing any work. They are just ticking, forever, like a clock that never needs winding. Then, in 2016, everything changed. Two separate teams of physicists, one at the University of Maryland and one at Harvard, announced that they had created the first time crystals in the laboratory. They were not the perfect, eternal time crystals that Wilczek had imagined. They were discrete time crystals, systems that were driven by an external force and responded with a period that was a multiple of the driving period. But they were real. They were proof that the concept was not just a mathematical fantasy. The world of physics was electrified. Time crystals were no longer a theory. They were a fact. But there was a catch. Those early time crystals were incredibly fragile. They existed only at temperatures near absolute zero, in systems that were exquisitely isolated from their environment. They were quantum systems, relying on the bizarre rules of quantum mechanics to maintain their delicate oscillations. Any disturbance, any stray photon or thermal vibration would destroy the time crystal instantly. They were beautiful, but they were also useless. They were laboratory curiosities, not practical technologies. That was the state of the field until June of 2026. And then everything changed again. In a paper published in the journal Nature Communications on June 24, 2026, an international team of researchers from Hiroshima University in Japan, the University of Colorado Boulder in the United States, and other collaborators announced a discovery that has sent shockwaves through the physics community. They have created space-time crystals, the most exotic form of time crystal, using everyday liquid crystal materials at room temperature. They have built a time crystal that is tough, durable, and stable, a time crystal that can exist in the messy, noisy world of a regular laboratory, a time crystal that could, in the near future, be used in practical devices. This is not just a scientific breakthrough. It is a technological revolution waiting to happen. Let me walk you through what they did, because it is a masterpiece of experimental physics. The team started with a liquid crystal material, the same kind of fluid that is used in the screens of your smartphone and your television. Liquid crystals are strange materials. They flow like liquids, but their molecules are arranged in a regular crystalline order. They are the perfect bridge between the fluid and the solid state. The researchers doped this liquid crystal with ionic substances, adding charged particles to the mix. Then, they applied a rhythmic, repeating electrical signal to the fluid. They were essentially driving the system with a regular beat, like a drummer keeping time. And then, something astonishing happened. Using advanced computer models and optical microscopes, the researchers observed a phenomenon known as period doubling. Even though the electrical drive pumped energy into the fluid at a set internal rhythm, the liquid crystals spontaneously locked into a pattern that repeated only every 2 cycles of the electricity. The system was responding to the drive, but it was doing so in a way that broke the symmetry of time. It was a time crystal. The liquid crystal was oscillating at half the frequency of the driving force, creating a repeating pattern in time that was independent of the input. But here is where it gets really strange. The researchers discovered that this unique rhythm is driven by the motion of tiny localized structures in the fluid, called topological solitons and disclinations. In liquid crystals, topological solitons are smooth, permanent twists that travel like stable wave packets through the material, whereas disclinations are sharp lines of structural mismatch where the neat alignment of molecules completely breaks down. As the voltage shifts, these microscopic features continuously transform, destroy, and recreate one another. They are like tiny whirlpools in a stream, constantly appearing and disappearing, but always maintaining the overall pattern. And here is the most mind-bending part of all. These shifting states behave exactly like the particle-antiparticle pairs of Majorana particles, a famous elusive class of quantum particles that are their own antiparticles. In this classical liquid crystal system, the researchers have created a real-world analog of these exotic quantum objects. The topological solitons and disclinations are dancing in a way that mirrors the behavior of some of the most mysterious particles in the universe. It is as if the liquid crystal is a classical simulation of a quantum phenomenon, a macroscopic window into the microscopic world. Now, let me put this in perspective. The early time crystals were quantum systems. They existed at temperatures near absolute zero in carefully controlled environments. They were like delicate snowflakes, beautiful but fleeting. The new space-time crystals are classical. They exist at room temperature. They are made of materials that are already used in trillion-dollar industries. And they are incredibly tough. The team found that the crystals remained perfectly stable even when they intentionally disrupted the electrical timing by up to 20%. Furthermore, they observed this synchronized, looping behavior continuing smoothly for over 24 hours. This is not a fragile curiosity. This is a robust, durable, practical phenomenon. What does this mean for the future? The possibilities are staggering. Because liquid crystals are already a staple of modern electronics, these durable, controlled space-time crystals could be used to design next-generation optical devices. Imagine reconfigurable laser elements that can be tuned in real time. Imagine advanced beam deflectors that can steer light with unprecedented precision. Imagine ultra-precise light steerers that can manipulate photons with the accuracy of a time crystal. The researchers are already talking about a brand new field that they call time liquid crystallinity, where fluid-like materials can be organized over time rather than just in space. We are not just building new devices. We are building a new way of thinking about matter itself. Now, let me take a step back and connect this to the grand tradition of physics. Richard Feynman was a man who was obsessed with the idea that the universe is understandable, that it follows rules that we can discover and use. He was also a man who loved to play with the ordinary, to find the extraordinary hidden in the mundane. He would have been absolutely captivated by this discovery. Here, we have a phenomenon that was once thought to be the exclusive domain of quantum mechanics, a phenomenon that seemed to require the most extreme conditions imaginable, And it turns out that you can create it with a liquid crystal and an electrical signal on a lab bench. The universe, it seems, is even more inventive than we thought. Think about what this means for the concept of a time crystal. For years, physicists debated whether time crystals were even possible. They seemed to violate the laws of thermodynamics. They seemed to be a mathematical trick, not a physical reality. But now we have not just one type of time crystal, but a whole new family of them. We have space-time crystals that are robust, durable, and practical. The concept has moved from the realm of theory to the realm of engineering. And there is an even deeper lesson here. The researchers discovered that their space-time crystals are driven by topological solitons and disclinations, structures that are themselves deeply connected to the mathematics of knots and topology. Topology is the branch of mathematics that studies the properties of objects that are preserved under continuous deformations. A coffee cup and a donut are topologically equivalent because you can deform one into the other without tearing or gluing. Topological solitons are like knots in a field, stable structures that cannot be undone without breaking something. The fact that these topological structures are the engine of the space-time crystal is a beautiful example of how the deepest mathematics is also the most practical physics. Hanqing Zhao, the first author of the study and a postdoctoral researcher at the International Institute for Sustainability with Knotted Chiral Metamatter in Japan, put it perfectly. Electrical switching of liquid crystals is at the heart of today's trillion-dollar liquid crystal-enabled industries. And realizing time crystals and liquid crystals may likewise lead to practical applications that could benefit everyday life in the near future. He is not just making a scientific statement, he is making a prediction about the future. The liquid crystal display is the foundation of the modern world. It is in your phone, your laptop, your television, your watch. And now, the same material that has given us the screen revolution is about to give us the time crystal revolution. Let me try to give you a sense of what this might look like in practice. Imagine a laser that can be reconfigured on the fly, changing its wavelength and its intensity in response to an electrical signal. Imagine a beam deflector that can steer light with the precision of a time crystal, creating images that are sharper and clearer than anything we have today. Imagine a new generation of optical computers that use light instead of electrons, processing information at the speed of light itself. These are not distant dreams. These are the near-term possibilities that emerge from this discovery. And then there are the long-term possibilities. The researchers have shown that complex space-time symmetries are not restricted to the quantum world. They can emerge in open, classical soft materials. This means that the principles of time crystallinity could be applied to a wide range of materials and systems. We could create time crystals in polymers, in colloids, in biological tissues. We could create materials that organize themselves not just in space, but in time, creating new kinds of structures and functions that we cannot even imagine. The discovery of room temperature space-time crystals is a reminder that science is not a straight line. It is a branching tree, full of unexpected connections and surprising detours. The researchers were not trying to create a time crystal. They were studying the behavior of liquid crystals under an electrical drive. They were exploring the physics of topological solitons and disclinations. And in the process, they stumbled upon something far more profound. They discovered that the universe is even stranger, even more beautiful, and even more useful than we had ever imagined. So, the next time you look at your smartphone screen, think about the liquid crystals inside it. Think about the fact that those same crystals can now be used to create time crystals. Think about the fact that you are holding in your hand a material that is capable of breaking the symmetry of time itself. And think about the fact that we are living in a golden age of discovery, a time when the boundaries between the quantum and the classical, between the theoretical and the practical, are being erased. This is the spirit of Feynman's Curiosity Lab. We do not just learn about the universe, we build it, we play with it. We find the extraordinary hidden in the ordinary. And we never stop asking, what happens if I do this? The discovery of room temperature space-time crystals is a testament to the power of curiosity. It is a testament to the fact that the universe is full of surprises and that the best way to find them is to look where no one else is looking. The researchers who made this discovery were not following a well-trodden path. They were exploring the unknown, asking questions that had not been asked before, and they found something that will change the way we think about time, matter, and the nature of reality itself. This is Feynman's Curiosity Lab. Stay curious, keep asking why, and never stop exploring. The universe is full of time crystals, and we are just beginning to learn how to use them.